Hello everyone, thank you for your attention.
Hello everyone, thank you for your attention. I'm HeKun from Shenzhen University and IJTCS. The title of my talk is Lovasz local lemma, variable and quantum. In this talk, I will concentrate on new versions of local lemma, including the variable version and the quantum version. The paper on variable version of Lovasz local lemma is joined with Li Liang, Liu Xingwu, Wang Yuyi, and Xia Mingqi, and the paper on quantum Lovasz local lemma is joined with Li Qian, Shen Xiaoming, and Zhang Jiapeng. In this talk, I will first give a brief review of related background. Then, I will present our main results. In the next, I will present the tight condition for variable Lovasz local lemma. Then, I will show the idea of the proof for that Scherer's bond is tight for quantum Lovasz local lemma. At last, I will conclude this report with some open problems. Firstly, let's give a brief review of the background. Lovasz local lemma is an important probabilistic method proposed by Erdős and Lovasz in 1975. It has many applications in combinatorics, probability theory, and theoretic computer science. Lovasz local lemma is to solve the following problem. Given a set of body events A1 to AN, could we avoid all these events simultaneously? Two properties of these events are considered in Lovasz local lemma. One is their probabilities, the other is their dependency relationship. Usually, the dependency relationship between these events is given with dependency graph. Dependency graph is an undirected simple graph in which each node is corresponding to an event, such that each event is independent of its non-neighborhood. For example, in this graph, A3 is independent of A4. Lovasz local lemma has many applications. Let's illustrate its application with the famous SAT problem. In this instance, there are three variables. We regard these variables as independent Bernoulli variables. Then, we can define a body event for each clause. If a clause is false, given the random assignment of variables, then the corresponding body event occurs. Thus, an event occurs with probability 1/4. It's easy to verify that the dependency graph of these body events is a triangle. Because all these events are dependent, one can also verify that this instance of set is satisfiable if and only if all the body events do not occur. Thus, we can apply the Lovasz local lemma to check whether a set instance is satisfiable. In other words, a mission of Lovasz local lemma is to depict the interiors of dependency graphs. Given a dependency graph GD, its interior is defined as the set of probability vectors P, such that any body events with a dependency graph GD and a probability vector P can be avoided simultaneously. We denote the interior of a dependency graph GD with int GD. For example, for this dependency graph, its interior is all the probability vectors below this triangle. The Lovasz local lemma depicting the interiors of dependency graphs is called the abstract Lovasz local lemma, since the dependency graph does not provide how the events depend on each other. Given a graph GD, many sufficient conditions that a vector is in the interior of GD have been known, such as this symmetric condition given by Scherer and this asymmetric condition given by Spencer. The ultimate condition of the abstract Lovasz local lemma is also given by Scherer with the independence polynomial. It's usually called Scherer's bond. Scherer's bond is closely related to the lattice gas partition function in physics. The abstract Lovasz local lemma has many variations. On the one hand, the dependency relationship can be depicted by some structures other than the dependency graphs. Some variations include the lopsided version and the variable-generated unit system. On the other hand, the abstract Lovasz local lemma only provides the existence of solution. The constructive Lovasz local lemma further provides efficient algorithms for searching the solutions in different settings. The variable-generated unit system is an important variation in both directions, because it fits for almost all Lovasz local lemma applications and is also the focus of the constructive Lovasz local lemma. Let's illustrate the variable-generated events with the set instance. A variable-generated unit system consists of a set of independent random variables and a set of but events. These but events are determined by these variables. The relationship between these variables and events can be modeled by an event variable bar graph. An event variable bar graph is a bipartite graph. One part of nodes are the events, and the other part of nodes are the variables. For any two nodes A and X, where A is an event and X is a variable, A and X are not connected by an edge if and only if the event is independent of the variable. For example, the event variable bar graph of the set instance is this. The node A1 is not connected to the node X3 since the event A1 is independent of the variable X3. Given an event variable bar graph, we define its base graph as follows. For any two events A1 and AI and J, if they depend on a common variable, then they are connected in the base graph. We can verify that the base graph is a dependency graph of these events. For example, the base graph of this instance is this. The node A1 and A2 are connected, since the events A1 and A2 both depend on the variable X2. The mission of variable Lovasz local lemma is to determine the interiors of event variable bar graphs. Given a bar graph GB, its interior is defined as the set of probability vectors P such that any but events with event variable bar graph GB and the probability vector P can be avoided simultaneously. We denote the interior of a bar graph GB with int v GB. For example, the interior for this event variable bar graph is all the probability vectors below this surface. An easy observation is that int GD_GB is a subset of int v_GB. In other words, given an event variable bar graph GB, the shearers bound of its base graph is contained in the bound of variable Lovasz local lemma. The variable setting is the focus of the constructive Lovasz local lemma. The famous Moser-Tallis algorithm is the most important algorithm of Lovasz local lemma, which searches the solutions in the variable setting. For the lower bound, it has been proved that Moser-Tallis algorithm converges efficiently in int GD_GB. For the upper bound, the convergence condition cannot be on int v_GB. Thus, we naturally want to know whether int v_GB is equal to int GD_GB. If not, what is it? Let's summarize the results on classical Lovasz local lemma. It has been proved that shearers bound is tight for the abstract Lovasz local lemma. Variable Lovasz local lemma is an important variation that fits for almost all applications. But the tight condition of variable Lovasz local lemma is unclear. It has been shown that the famous Moser-Tallis algorithm converges efficiently in shearers bound. But the tight condition of convergence is also unclear. The classical Lovasz local lemma can be naturally extended to the quantum version. The goal of classical Lovasz local lemma is to avoid the bad events in probability space. Analogously, the goal of quantum Lovasz local lemma is to avoid the bad subspaces in the Hilbert space. Let S be a finite dimensional Hilbert space. The bad events in probability space are analogous to the bad subspaces in the Hilbert space. The probability of an event is analogous to the relative dimension of a subspace, where the relative dimension of Si is defined as the dimension of Si over the dimension of S. To avoid all these subspaces, we should prove the existence of a state psi, which is orthogonal to all bad spaces. Since a classical event does not occur is analogous to that, the state psi is orthogonal to the subspace. Thus, analogous to the variable-generated unit system, we can also define the local Hamiltonian system. A local Hamiltonian system consists of a set of QDs and a set of Hamiltonians. The QDs span a Hilbert space, and the local Hamiltonians can be regarded as subspaces of the Hilbert space. For example, this is a system with 3 QDs and 3 local Hamiltonians. The relationship between the QDs and the subspaces can be modeled by the interaction bigraph. An interaction bigraph is a bipartite graph. One part of nodes are the subspaces, and the other set of nodes are the QDs. For any two nodes S and H, where S is a subspace and H is a QD, S and H are not connected by H if and only if the subspace does not rely on the QD. For example, the interaction bigraph of these local Hamiltonians is as this. The node S1 is not connected to the node S3 since the subspace S1 does not rely on the QD S3. Given an interaction bigraph, we can also define its base graph. For any two subspaces, Si and Sj, if they rely on a common QD, then they are connected in the base graph. For example, the base graph of the system is as this. The nodes S1 and S2 are connected since these two subspaces depend on a common QD, S2. The mission of quantum Lovasz local lemma is to depict the quantum interiors of interaction bigraphs. Given an interaction bigraph GB, its quantum interior is defined as the set of relative dimension vectors R, such that any subspace with interaction bigraph GB and relative dimension vector R cannot span the whole space. We denote the quantum interior of a bigraph GB with int Q GB. For example, for this interaction bigraph, its interior is all the relative dimension vector below this triangle. An easy observation is that int QGB is a subset of int VGB, since classical events are spatial subspaces. Given a bigraph GB, many sufficient conditions that a vector R is in the quantum interior of GB have been known, such as this symmetric condition and this asymmetric condition. It also has been proved that Scherer's bond is in the quantum interior. Formally, int GD-GB is a subset of int Q-GB. Moreover, it's conjectured that these two bonds are equivalent. In other words, Scherer's bond is tight for quantum Lovasz local lemma. The quantum Lovasz local lemma has many applications. In physics, most systems of physical interest can be described via local Hamiltonians, and quantum Lovasz local lemma can be used to determine whether local Hamiltonians are frustration-free. In computer science, causality problem is the most important issue of quantum complexity, and quantum Lovasz local lemma can be used to determine whether a causality instance is satisfiable. The quantum Lovasz local lemma has been used to improve the bonds about k coset and random k coset. It's also used to calculate the critical threshold when a local Hamiltonian must be frustration-free. Moreover, Jane and Thata proposed a constructive quantum Lovasz local lemma which defines a satisfiable psi in Scherer's bound. Between the classic version and the quantum version, there is also a commuting version of local lemma. In commuting Lovasz local lemma, only commuting subspaces are considered. The commuting Lovasz local lemma also has many applications, such as the toric code. The mission of commuting Lovasz local lemma is to depict the commuting interior of interaction bigraphs. We denote the commuting interior of a bigraph GB with int cGB. An easy observation is that int cGB is between int vGB and int qGB. Let's summarize the results on quantum Lovasz local lemma. It has been proved that Scherer's bound is in the quantum interior. The tight condition of commuting Lovasz local lemma is between the conditions of quantum and variable local lemma, but the tight conditions of quantum commuting and variable Lovasz local lemma are all unclear. In the following, we present our main results. For variable Lovasz local lemma, we propose a mathematical programming exactly depicting int vGB. This gives the tight condition of a variable Lovasz local lemma. We also show that for most bigraphs GB, int GDGB is a proper subset of int vGB. In other words, variable Lovasz local lemma is usually beyond Scherer's bound. Our results make it possible that Moser-Tallis algorithm is efficient beyond Scherer's bound. For quantum Lovasz local lemma, we prove that Scherer's bound is tight. This proves the conjecture of Thata and his co-authors. Our result implies that Gehen's-Thata algorithm is tight for quantum Lovasz local lemma. In physics, our result also implies that the lattice-Gas partition function provides a complete characterization of quantum satisfiability for almost all Hamiltonians with large enough QDs. For commuting Lovasz local lemma, we prove that it goes beyond Scherer's bound. This makes it possible that Gehen's-Thata's algorithm can be efficient beyond Scherer's bound for commuting subspaces. Our results can be summarized in this figure. We prove that Scherer's bound is tight for quantum Lovasz local lemma, and we also give the tight condition of variable Lovasz local lemma. The tight condition of commuting Lovasz local lemma is still unclear, but we prove that it goes beyond Scherer's bound. We also calculate the bounds of different Lovasz local lemmas on lattice. Here, PA is the threshold of abstract Lovasz local lemma if the vector that all entries are PA is exactly on the bound of abstract Lovasz local lemma. Similarly, we can also define the thresholds PV, PC, and PQ. These thresholds on different lattices are shown in the table. In the following, I will present the tight condition for variable Lovasz local lemma. Note that determining the variable interior is equivalent to determining its boundary. Here, a vector P is on the boundary of variable interior if and only if for any epsilon larger than 0, 1 minus epsilon multiple this vector is in int vGB, and 1 plus epsilon multiple this vector is not in int vGB. Intuitively, a boundary vector in some direction is the minimum probability vector such that the events cannot be avoided simultaneously. For example, for this event variable bigraph, the boundary of variable interior is all the vectors on this surface. For the boundary vectors, we can prove the following discretization theorem. For the boundary vectors, there exists a set of events which cannot be avoided and satisfy an extra constraint that each variable only takes d values, where d is the degree of the variable in the event variable bar graph. The discretization theorem has many applications. We have applied it to calculate the boundary vectors of all cycles and the thresholds of variable Lovasz local lemma on many lattices. The discretization theorem has a clear intuition from the geometric perspective. If the random variables x1 to xn are uniformly random on the interval between 0 and 1, then the probabilistic space is analogous to a hypercube. The event in the probabilistic space is analogous to the cylinders in the hypercube. The probability of an event is analogous to the Lebesgue measure. The event variable bar graph in its GB is analogous to that the cylinders conform with GB. The word conform means that the cylinders cannot use irrelevant variables. For example, in this bar graph, event A2 is independent of variable x1. Then cylinder A2 should be consistent in the dimension of x1. Thus, a probability vector P is in the interior of GB is analogous to that any cylinders with bar graph GB and a probability vector P cannot fulfill the hypercube. Thus, according to the discretization theorem, we have that for any boundary vector P, there is a set of cylinders fulfilling the hypercube under the extra constraint that each unit interval is partitioned to d segments. For example, for this bar graph GB and each vector P on the boundary, we can construct a two-discrete system of cylinders with GB and P such that the hypercube is covered by the cylinders. Each unit interval is partitioned to two segments, and the cylinders are confirmed with the bar graph. We can formalize the intuition of our theorem with the following mathematical programming. For any direction P and lambda larger than 0, lambda P is on the boundary if and only if lambda is the solution to the mathematical programming. These constraints guarantee that the unit interval in each dimension is partitioned to these segments. The cylinders cover the hypergraph, and the cylinders conform with the bar graph. Lambda is minimized to make that the vector lambda P is exactly on the boundary. In the following, we will prove that Scherer's bond is tight for quantum Lovasz local lemma. We will illustrate the idea of our proof with this interaction bar graph. It's easy to verify that its base graph is a cycle of length 4. One can also verify that for any epsilon larger than 0, 1 minus epsilon multiple the vector double 1 over 3 double 1 over 4 is in int gd gb, and 1 plus epsilon multiple this vector is not in int gd gb. In other words, the vector is on Scherer's bond of gd gb. To prove that Scherer's bond is tight for quantum Lovasz local lemma, we need to prove that the vector is also on the bond of quantum Lovasz local lemma for GB. In other words, we need to show that for any epsilon larger than 0, 1 minus epsilon multiple this vector is in int QGB, and 1 plus epsilon multiple this vector is not in int QGB. The first part has been proved by Satas and his co-authors. Since they proved that Scherer's bond is in the quantum interior and this vector is in Scherer's bond, thus we only need to prove the second part. which is equivalent to prove that there exists subspace with relative dimension double 1/3, double 1/4, spanning the whole space. We prove this conclusion by induction. Our inductive assumption is that for any bigraph with no more than 3 nodes, shortest bound is tight for quantum Lovasz local lemma. For this subgraph, one can verify that the vector 1/3 double 1/4 is on shortest bound. By shortest bound is tight for quantum Lovasz local lemma, we can assume that subspace with relative dimension 1/3 double 1/4 can span the whole space. A tool used in our proof is the geometrization theorem, given by graph GB, dimension vector D of QDs, and the relative dimension vector R of subspaces. If there is a set of subspaces of this setting spanning the whole space, then the random subspaces of the setting also span the whole space with high probability. In other words, if there exists such a set of subspaces spanning the whole space, then almost all such spaces spanning the whole space. With the geometrization theorem, we can assume that for this subgraph, random subspaces with relative dimension 1/3 double 1/4 span the whole space with high probability. Now, let's return to the proof. We prove this conclusion by constructing such a set of subspaces. Recall that H1 to H4 are QDs, and S1 to S4 are subspaces. Without loss of generality, we assume that H2 is a qubit. In other words, H2 has 2 dimensions, E1 and E2. Let S1 be E1, tensor V1, tensor H3, tensor H4. Here, V1 is a subspace of H1 with relative dimension 2/3. Then, S1 only relies on H1 and H2, and its relative dimension is 1/3. Similarly, let S2 be E2, tensor V2, tensor H1, tensor H4. Here, V2 is a subspace of H3 with relative dimension 2/3. Then, S2 only relies on H2 and H3, and its relative dimension is 1/3. Let S3 be V3 tensor H1 tensor H2. Here, V3 is a subspace of H3 tensor H4 with relative dimension 1/4. Then, S3 only relies on H3 and H4, and its relative dimension is 1/4. Similarly, let S4 be V4 tensor H2 tensor H3. Here, V4 is a subspace of H1 tensor H4 with relative dimension 1/4. Then, S4 only relies on H1 and H4, and its relative dimension is 1/4. In summary, the relative dimensions of S1 to S4 is exact 1/3 and 1/4, and their base dependence graph is exact the cycle of length 4. Let's consider the subspace E2 tensor H1 tensor H3 tensor H4. Obviously, S1 is not in this subspace. And in this subspace, E2 is completely contained in S2, S3, and S4. In other words, the 3 subspaces do not rely on E2. Only S4 relies on H1. One can prove that deleting the QDs only used by one subspace does not change the bounds. Therefore, it's lossless to delete H1. Thus, the base dependence graph of S2, S3, and S4 is a path of length 3. By our inductive assumption, we have random subspaces with relative dimension 1 over 3 double 1 over 4 span the whole space with high probability. Thus, S2, S3, and S4 span E2 tensor H3, tensor H1, tensor H4 with high probability if V2, V3, and V4 are random. Similarly, let's consider the subspace E1 tensor H1, tensor H3, tensor H4. Obviously, S2 is not in this subspace. And in this subspace, E1 is completely contained in S1, S3, and S4. In other words, the three subspaces do not rely on E1. Only S3 relies on H3. Therefore, deleting H3 does not change the bound. Thus, the base dependence graph of S1, S3, and S4 is a path of length 3. By our inductive assumption, we have random subspaces with relative dimension 1 over 3 double 1 over 4 span the whole space with high probability. Thus, S1, S3, and S4 span E1, tensor H1, tensor H3, tensor H4 with high probability if V1, V3, and V4 are random. In summary, if V1 to V4 are random, then S2, S3, S4 span E2, tensor H1, tensor H3, tensor H4 with high probability, and S1, S3, S4 span E1, tensor H1, tensor H3, tensor H4 with high probability. By union bound, we have that if V1 to V4 are random, then S1 to S4 span the whole space with high probability. Thus, we can obtain a set of subspecies with relative dimension double 1 over 3 and double 1 over 4 spanning the whole space, which finishes the proof. Let's review the proof. Given a relative dimension vector on Scherer's bond, we need to construct a set of subspaces with this vector spanning the whole space. The method is to decompose the graph by partitioning the dimensions of some qubit. Then, to show the existence of such subspaces on the original graph, we only need to prove that random subspaces of each subgraph span the whole space in each partition with high probability. This is proved by the inductive assumption and the geometrization theorem. To prove the theorem on general graphs, we can also decompose the graph by partitioning the dimensions of some qubit, such that each subspace relying on the qubit is only contained in a subgraph and considered in a partition. In each partition, we can obtain random subspaces spanning the whole space by the inductive assumption and the geometrization theorem. To obtain the desired subspaces in the original graph, we assemble the subspaces in each partition. By applying the random and the constructive iteratively, we obtain a complete proof. To apply the inductive assumption in each partition, we need that the relative dimensions of subspaces in each partition is also on the Scherer's bond of each subgraph. Thus, we determine the relative dimension of each partition of the qubit carefully with the independence polynomial. Finally, let's conclude this report with some open problems. We prove that Scherer's bond is tight for quantum Lovasz local lemma, and we also give the tight condition of variable Lovasz local lemma. The tight condition of commuting Lovasz local lemma is still unclear, but we prove that it goes beyond Scherer's bond. Our results have many implications, including getting Sata algorithm is tight for quantum Lovasz local lemma, and lattice-Gas partition function characterizes quantum satisfiability. Our results also show the power of quantum from the view of Lovasz local lemma, because we proved that variable Lovasz local lemma goes beyond the bound of quantum Lovasz local lemma. The Moser-Tallis algorithm is based on the variable setting, though we have proved that variable Lovasz local lemma goes beyond Schur's bound. The convergence condition of Moser-Tallis algorithm has not yet broken Schur's bound. An interesting problem is whether the Moser-Tallis algorithm still converges efficiently beyond Schur's bound. Though we have proved that commuting Lovasz local lemma goes beyond Schur's bound, its tight condition is still unclear. Another interesting open problem is whether the commuting Lovasz local lemma is equivalent to the variable version. In the quantum and commuting Lovasz local lemma, only the interaction by graph and the relative dimension vector of subspaces are used. Actually, the dimension vector of QDs is also an important factor for whether the subspaces span the whole space. What's the condition for the existence of satisfiable states with all these three factors? That's all for my talk. If there are any questions, I would like to give further explanations. Thank you.
Okay, thanks, Kun, for the nice talk. So here are some questions from the audience. Let me see. The first question is like relative dimensions of discrete values. How to understand A log L equals to QL given this fact?
Okay. Obviously, relative dimensions are discrete, or they are rational. So we say abstract Lovasz local lemma is equivalent to quantum Lovasz local lemma. We only consider the rational numbers. If the rational set are if the rational sets are the same, then we think they are equivalent. Moreover, we can also define the Hilbert space with infinite dimensions, but the mathematics is much more complex. We only consider the rational numbers in our paper.
Okay, thanks. So the second question is that the cylinder analogy in the proof is marvelous. So I want to know whether there are any other application of this technique.
In our, I think the cylinder is very intuitive in our proof, since the geometry perspective is a simple, just a simple tool used in our proof. It's not very different from the original view of Lovasz local lemma. We don't know any other application of this technique.
Okay, thanks. So if there's no more questions, then let's thank Kun He again. And that ends the talk of Dr. Kun He. Thanks.
Okay, thank you.